Right, welcome. Today is the second lecture on OVS networking. So last week I went through all of the basics of installing the software onto our computers, and this week I will explain the networking aspect of how you will actually build your virtual network inside your cloud itself. So as you all know, we're all working on subnet 28. So all of our computers are physically connected onto network 28 in the lab. Network 28 means that your IP addresses will start with 148.197 as they always will, and they belong to subnet 28. So our computers are physically on subnet 28, and then our Prometheus virtual machines are bridged once onto subnet 28 as well. The convention that we use is that the IP address that you have on your Prometheus virtual machine will be whatever your IP address on your computer is plus 100. So beyond that, other than subnet 28, we do have some few other subnets available to use as well. We have subnets 30, 31, and 32. So the way that we will use this is if we scroll down on the lab sheet itself, we have created in OVS the bridge for VMnet 28. That contains a net28 network card that connects you to the outside world, and then it also contains an ENS33 network card or to where this bridge is connected. So think of it as that, like this. The bridge is called VMnet 28, and it has two ports, two edges to the bridge, which is net 28 on the one side and ENS33 on the other. So now this allows anything that is on network 28 to be able to connect to the internet straight away because it's a bridged connection. So anything that's built on network 28 will essentially have direct connectivity to the outside world, and we don't need to do anything else about it. Other than that, in the next part of this, we have also gone and created VMnet 30, 31, and 32. Now these network cards will be in a sort of host-only basis, as we call it. So they will have their own IP addresses. They will be on different subnets. You have an allocated range of IP addresses to use for all of them, and we need to explain exactly how we actually go about doing this. We need to have a way in place so that you don't all use the same IP addresses. The way that we do this is by using a file that is called a2.net subnets. Now, on this file, we have what? We have subnet 30, which starts at 148.197.30.0 and goes all the way down to 30.255. Okay, so this is an entire class C network, essentially. In here, we can have 254 computers. All right, it goes up to 255, 0 counts as well. So we have 256 combinations, 256 different numbers that we can use for this. Because we need to have a network address and a broadcast address. 0 is our network address, 255 is our broadcast address, and this is a standard Class C network. Okay, 30.0 to 30.255. Now, the same principles that I will explain here will also apply for networks 31 and 32. All we're changing is the number, 30, 31, 32. All right, so what we've done is we have 48 computers in the class. All right, we need to make sure that we divide those 256 unique numbers or 254 addresses among the 48 computers that we have in the lab, so that we make sure that you all get an allocated range of IP addresses that you can use. We've done this by actually creating 64 slices, 64 unique networks, and each of those networks belongs to each of the computers. So you can see the hosts, so we have computer names on the left, and then we have the line that corresponds to each of them. This goes all the way down for the 48 computers, and then we have some spare addresses, and then we have my computer at the very end. All right. Well, the spare ones are mine as well, but never mind, it's fine. So, we've managed to take our Class C network of 254 usable IP addresses and split it into so many slices as to make sure that we cover our needs, and our need is to have 48 networks, 48 computers in there. All right. Now, I will explain why we split it to 64 and not 48 later on. All right. So what happened with this is that the first computer, which is in the corner, in the far left corner of A2.NET, is Farina, and that can work on network 30.0 up to 30.3. It means that for Farina, the network address is 0, the broadcast address is 3, and the usable IP addresses in subnets 30, 31, and 32 are addresses 1 and 2. In exactly the same way, for everybody else, let's say, for example, if I was working on Lauda, my network address is 36, my broadcast address is 39, and then usable IP addresses for Lauda are 37 and 38. This means that if we have a network that can fit 2 IP addresses inside it, and we have 3 networks available to use, because we have subnets 30, 31, and 32, that gives us a total of 6 usable IP addresses for our cloud. Okay, so we can easily build 6 computers in our cloud that will be on public addresses in there, and once we set up routing on the host as well, they can be publicly accessible from anywhere on the internet. And I say public addresses because then we can also have as many private addresses as we like. Alright, so we can have private networks, we can NAT behind whatever we like, and so on. So there are other techniques to give us more IP addresses, but I will concentrate today on how we actually go about having those public IP addresses here. Now, what does this mean for our network settings? So if we go back into our lab sheet, in the same way that we created net28, we have also created, or we will eventually create, net 30, 31, and 32. So those network cards need to have all of the networking information on them that we need to have so that they actually work correctly. So going through the lines on this configuration file, the first things that you will need to do is you need to change the name and the device name for the network cards. So for those configuration files, instead of net28, they will now be called net30, net31, net32. And then we'll need to change the IP address. The IP address that we'll need to change will be all of this. So these network cards are no longer going to be on network 28. They will be on networks 30, 31, and 32. What address should we use? Let's say, for example, that we're doing net 30, and let's say, for example, that we're sitting on the computer, I don't know, MOS. So in order to figure that out, we can go into our list, and we can try to find MOS. It's this guy here, and MOS is working on a network address of 68, broadcast address of 71, so usable IP addresses for MOS are 69 and 70. Okay, so straight away we can say, all right, for MOS, for my net 30 network card, I will use 30.69. It's not wrong to use 30.70 because that is also an available IP address for you to use. It's just crazy. Okay? It's a little bit unreasonable. All right, so you have 2 addresses to allocate. The first one on your network structure on your network, make it the first one. Yes, you can fight the system and me and everything and use the second address if you like here. However, if you do call me to your computer to troubleshoot it, and any of my poor assistants, we will shout at you. All right. What we want, we'll just be upset. So, use the first IP address, yeah? So, once you have the address here, you need to change the prefix. And this is where all the fun begins. All right. Who can tell me what the prefix is in a network? subnet mask. Okay, so yes, 30 is the solution, yes, but we need to figure out why, yeah? So, on network 28, the prefix is 24, because I really don't know if I can do this and actually show it on the video. Let's talk subnet masks. Yes, so network 28 is a default class C network. What is the default class C subnet mask? Yes. All right. So there is a reason for the spacing, you see. Yeah. All right. So 255.255.250 is the default class C subnet mask. Why does it have a prefix of 24? 3 times 8, 24. 24 bits out of this are in use. Where do those 24 bits come from? From the fact that computers don't read decimal, they read binary. Yes? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So the binary form of our default class C subnet mask looks like this, out of which 24 bits tell us how long the subnet mask is. It's a 24-bit long subnet mask. Okay, so what happens when we take our little class C network and split it into 64 slices? Better yet, why 64 slices? Anybody, for 10 points. No? Go on.
Because it has to be a power of 2.
Exactly. All right. We're dealing in binary. So whatever we do needs to be a power of 2. All right. So the powers of 2 are 0, 1, 2, 4, 8, 16, 32, 64. We have 48 computers. We need 48 networks. Therefore, we need to split it into 64 slices. All right. 64 slices of 256 addresses. Yeah? This is division in Greece, by the way, so don't start telling me about it. All right. This gives us what? How many times can you fit 64 into 256? 4 times. This also means that because we can fit it 4 times, essentially we're talking that the number of bits that we're going to take out of this when we convert it from binary to decimal and so on will change. So this means that when we're going here, the number 4 basically represents the 4 numbers that we'll have in our network. Yes? So the easiest, most logical way to think about it is this. So 4 numbers in our network means a network address, a broadcast address, and 2 usable IP addresses. All right, 4 numbers. Because 4 times 64 is 256. So those 4 numbers, how many bits do we need in binary in order to do this? Yeah? So we have 0, 0, 0, 1, 1, 0, 1, 1. Okay, so now, out of all of these bits in the subnet mask, we don't need 8 bits anymore for our addresses. We only have 4 addresses. We only need those 2. Yeah? This means that these guys can now turn into 1s. All right, so our new subnet mask will be 8, 16, 24, 30. All right, so 30 bits on the subnet mask. So this means that going back into our file, this prefix needs to change into 30. Annoying coincidence that it's 30 and we're working on net 30. Yes? This will stay 30 for networks 31 and 32 as well. Yeah? Don't start renaming everything to 31 and change the prefix as well. Alright. This should always stay 30 because networks 30, 31 and 32 are of equal size, equal dimensions, same dimensions. Alright. So the subnet mask will become that. The prefix will become that. The gateway for this requires me to draw another diagram. And I'll do it here. So let's say that this guy is, come on, let's work on one of the computers and make it actual. In fact, let's work on my computer, why not? I am on 28.11, yeah? So this is Shumi, and I'm connected to the outside world by 28.11. Okay, with a network card that's called EN01. Now in here, I love playing with colors, I have my been let down by my marker. I have my Prometheus VM that has ENS33 that has an address of 28.111 that connects to EN01 and then takes me to the internet. Alright, in here, this ENS33 network card, alright, will be replaced. So it will be replaced by net 28. Okay, and my net 28 IP address will of course be 28.111. That's fine. Alright, same as before. I will keep having this ENS33 network card, but it will not have an IP address. So when I type ifconfig in a terminal on Prometheus, I should still see ENS33, but it should be blank, no IP address. And all of the information for this should now be moved on to net28. Now, because I'm going to create some more network cards, I'm creating nets 30, 31, and 32 on Prometheus itself. So I'm going to have 3 more network cards. I managed to make everything not fit. Hooray. I'm going to have net 30, net 31, net 32. Okay. So my ifconfig on my host, on my Prometheus machine, should show all of these guys by the end of this lab set. And this is accomplished by adding them in OVS, by adding the bridges. Okay, so I'm going to have this set of commands for networks 28, 30, 31, 32, and creating the config files, just like I've created here ifcfg net 28. I will also need to have net 30, 31, 32, which is the file zone that we're working on at the moment. Okay, so if I'm making this example for my computer is at the very end of this. So my first usable IP address is 253. So I'm going to have 30.253, 31.253, 32.253. They should all be the same because they are the same address but on a different subnet. Alright, so different IP address really. So I have these guys and then I'm building a cloud. That looks like an amoeba, but never mind. So once I have these network cards on Prometheus itself, I need to go inside my cloud and build the other network cards in there as well. Before I do that, because I seem to have forgotten what I was actually doing, gateway. Yeah? The gateway for these guys will actually be the guy that takes you to the internet, to the outside world. So the gateway for your net 30, 31, 32 will always be your 28 something IP address on your net 28. All right. This means that because you're going from networks 30, 31, 32 onto network 28, everything back here will no longer have internet access. Yes, we're jumping across different subnets. Therefore, for this to work, we need routing. And the routing that we need to use is OSPF. Okay, and I will explain that as well. So, gateway for these guys onto this file will be whatever IP address you have for your net 28 network card. The DNS server will stay the same for everybody always. Okay, we have one DNS server in the class and that's it, basically. So, now that we have the network cards configured onto Prometheus itself, we need to move inside the cloud. And we need to move inside the cloud and configure the network devices in there. So we need to go into our Sandstone interface, we need to go into networks, and we need to delete the existing BR0 bridge that's in there. Okay, and if you made another network card because you basically create the network card to add it onto the virtual machine and then remove it, then you need to delete that as well. So at this point, delete everything in your networks inside your virtual machine, inside your cloud. You will need to create 4 bridges. The bridges will be net 28, 30, 31, 32. And they will look like, this is not going to fit. So net 28, 30, 31, 32. So this will be inside the cloud. What IP addresses do I give to these guys? So obviously my net 28 network card is double bridged. All right. So the rule that we use is our IP address plus 100 plus another 50 if I can get to it. Yeah. So I'm using 111, so I can do 161 for myself here. 161, and I'm okay. You can either do plus 50 or minus 50, and if everything conflicts with anything else, then you need to tell me. All right, you need to ask either me or one of my assistants, and we'll work out an IP address for you, because the problem is that the IP addresses are semi-randomly allocated in the lab. So I need to basically restructure my subnet 28 in the lab, and I'm trying to convince my administrators to do this for a couple of years now, but they don't want to. So yeah, all right. So make sure you ask us before you allocate an IP address inside the cloud. What about 30, 31, and 32? What IP addresses will need to go on here? The second usable IP address, yeah? So if I go back into A2.NET subnets, I've allocated 253 already, so I can use 254 for my network cards in here. All right. Gateway for my network 28 network card. It's bridged like all of the other net 28 network cards. So because it's a bridge, the gateway will remain the same. 28, 254. Yeah? Subnet mask for this default class is subnet mask, and the DNS server is the DNS server. What about these guys? The rule generally is that your default gateway for a network interface is the next IP address or the next network card you see on your way towards the internet. So for these guys, the gateway for the second address is the first address. Okay, so gateway for these are these. Obviously the 30 to the 30 and the 31 to the 31 and so on. Yeah? So we have the default gateway for this. What about the subnet mask? What will the subnet mask be in here? We need to change it because it's not a default class C network anymore, because we've messed around with the bits that are up there. So now we need to know what the default subnet mask will be after the changes we've made for our smaller network. So we go back to our subnet mask, and we have these guys here. So these are now enabled, they are ones, so now they count towards our subnet mask. how do we turn binary into decimal? We're 8 bits. 1, 2, 8, 64, 32, 16, 8, 4. Add them all up. Okay, and this is actually mentioned on the bottom of this. So when you're configuring your network cards in here, not the 28, the 30, 31, 32, the subnet mask that you'll need to use is 255, 255, 255, 252. All right. The gateway is whatever the gateway is, whatever the IP address you have here, and the DNS server is obviously the same, 28.1. I highly recommend that you all make this network diagram a little bit more presentable maybe in your logbooks. Okay, and do it before you actually attempt to allocate IP addresses to network cards. All right, because you can use this as a map in order to figure out what IP addresses you need to be using everywhere so that you don't actually make any mistakes. All right. Yes, if you do make a mistake, it's not the end of the world. We can make the changes and restart everything and done. It's fine. But we need to make sure that you are actually using the correct IP addresses everywhere. All right. So now that you have configured all of the network cards on the host, you configure the network cards in the cloud itself, you have a working network inside Prometheus, we need to give these guys internet access. In order to do this, we'll need to go to the last part of the lab sheet and do some routing. Funny games. All right. Now, you can turn a Linux PC into a router by using Zebra, which is actually now called Quagga. They have a thing for animals, I don't know why. All right. So, Zebra is the routing daemon, the program that actually does the routing in Linux. All right. We need two components to make this work. We need the software, so we need Zebra, and we need the routing protocol as well. In our case, we will be using OSPF. All right. Nice, simple interior gateway protocol. All right. In order to do this, we need to have a few things in place. First of all, we need to have Quagga installed. So yum install Quagga will make sure that your Prometheus, all of this is happening on Prometheus, by the way, yes? Nothing inside the cloud. So we need to make sure that we do yum install Quagga on Prometheus so that we get the software installed there and running. And then you need to go into the routing utils folder on Moodle and you need to get two files. One of them is called zebra.conf and the other one is called ospfd.conf. So the files look like this. Oh, come on. All right, can you read it? So, zebra.conf has the very basic job of telling the routing daemon which network cards we're doing our routing through. We are doing our routing through all of our network cards. So you need to mention net 28, 30, 31, and 32. Okay, very simple. And the wonderful fact is that you actually can download it, use it as this. You don't need to make any changes because we all have the same network cards. All right. The file that will need changes is ospfd.conf. Okay. Now, can you see this? I don't know. Can I make it bigger? What if I go to edit font? I can. Yeah, Control Plus. All right. So, in the ospfd.conf file, the first thing that we need to mention is our OSPF router ID. Okay, which computer will be the router? Everything that we mention in here is basically going to get transmitted onto all of our neighboring OSPF routers. So this is information that will be exchanged with all of our networking OSPF routers. In your case, in the lab, we're talking about Columbus, so the gateway to the lab. the computer that actually has an address of 28.254 and also 28.115. Okay, it's a binding network card with multiple IP addresses on it. And also 28.1 if you want to know. Yeah. 3 in 1, hooray. So, this means that we need to mention our own computer. So this means that you need your Prometheus's IP address. So in my case, I need to have 28.111. All right. This way, when this information is being transmitted to all of your neighbors, they will know where it's coming from. Okay. Now, we move on to networks. We need to mention all of the networks that are configured on the network cards that we mentioned in zebra.conf. So we need to advertise all of the networks that are directly connected onto our Prometheus computers. All right. So you will all be connected onto 28.0/24. Okay. You don't need to make any changes to this line. You should all have this line. And then we need to mention our networks 30, 31, and 32. And because these will be network addresses, these need to be, for my computer at least, it will be 252. Because if I go here back to my file, my network address is 252. Again, coincidence with a subnet mask. Yes? All right. So, on this file, you need to have your network address. And it will need to be the same for all of them. And that's it. There's 4 things that you need to change: your Prometheus IP address and the network address that corresponds to your computer according to the subnets a2.net file, and that's it. All right. So now your computer will know which networks to advertise, and we can go and we can type these lovely 4 commands. All right. It's 4 commands in one because they're, they have a semicolon in between them. So systemctl enable Zebra, systemctl enable OSPFD. This will set these guys up to start up every time you start your computer, your Prometheus. And systemctl start Zebra and OSPF will basically start the services running on your system. Once they are running, you will also need to disable the firewall. The easiest way to do this is to do iptables -F. All right. And in order to check this, you can do iptables -L, capital letters as well, okay? Because that will list your iptables rules. So you can disable your firewall by simply flashing the contents of the iptables. And you will also need to enable your packet forwarding onto your operating system, okay? Any Linux distribution by default ships out with packet forwarding disabled by default as a security measure. All right. The packet forwarding, you only need to do it once. The firewall, you need to do it every time you restart Prometheus. Okay. Once you do all this, you should then now be able to type root -N in a terminal, and you should be able to see your full routing table. It should include your networks 28, 30, 31, 32. If it's working correctly, it should include another 28.0 network, this time coming from 28.115, which is Columbus. And then if everybody else starts getting their routing going in the class, you should soon be able to see everybody else's network addresses show up. Okay. For networks 30, 31, 32. So eventually, by the end of, once everybody has configured this correctly, the routing table should have 48 times 4, really. Okay, number of networks on it. Good luck with that. All right. So you should be able to see everybody else's networks when they're working. And of course, the ultimate test in the end is that you boot up one of your virtual machines, you connect one of those network cards onto those virtual machines in the cloud, and you try to ping google.com from there. Once you can do that, it means that you've given the correct IP addresses here, and you set up routing correctly on Prometheus, and you can go on to the outside world. And now you have the networking infrastructure in place to actually start building your entire cloud. Okay. I expect this lab sheet to take you a week to do, one more week. Okay, so I'm expecting OVS to last 2 to 3 weeks, really. Okay, so don't stress and panic if you don't get all this going by the end of this week. Don't forget, we do have next week free, that we don't have any classes because it's consolidation week. I would recommend though that you don't really do any work on that week on the computers, all right? Only if you're really falling behind. Like I have students that started working in the lab last week. Okay, so if you are behind, then please come in during the consolidation week and work. If you are not, don't worry. I would rather that you concentrate it on your logbook. Okay, make sure that you have all of your screenshots in your logbook and that you have explanations for all of your screenshots in your logbook as well. All right, so in this logbook, in this screenshot, I'm doing this because that and that reason. Okay. When we get back after the consolidation week, we have 3 weeks remaining before the Easter break. And then when we come back after the Easter break, we have another 2 weeks of classes. So essentially, assuming that you get OVS out of the way before consolidation week, that leaves us with 5 weeks for the last lab sheet, which is more than enough. Yes? Again, the last lab sheet, I wouldn't expect it to take you more than 3 weeks to do. So progress-wise, there's plenty of time. Make sure that you understand everything that you're doing and that you actually learn something from the module, and don't just rush to complete all the tasks just for the sake of it. Okay, so make sure that you move at your own pace, you understand everything completely, and that should reflect on your logbook, which will then be reflected on the wonderful mark that you can get on it. Yeah? All right. Any questions about all this at all? All right. Yes.
So here we have used /30 network.
Mm-hmm.
Can we also use /31?
No.
No, in future.
Generally, sorry. Yes, you can use whatever you want, basically. So yes, on Moodle, you will find another link as well that I have uploaded. Okay, you will find this. This goes on to my favorite website, because I'm a nerd, yeah, which is firewall.cx. Okay, yes, thank you, Chrome. It's very smart. So you can go here and read all of this. Okay, so this starts on subnetting and talks about class A, B, C, and so on, and the number of bits that you can use and the networks that you can have and the numbers of classes that, you know, they all correspond to. And then eventually they do what I did on the whiteboard with more colors. Professionals. Fine. And that they just explain everything. Yes? So if you go on to this, I would really recommend that you read everything in the networking section of this website. All right. Very nice. Really recommend it. Okay, so yes, you can use a different combination of subnet masks, whatever you want. It all depends on the size of the network that you are building, and that's basically how big ISPs deal with IP address shortages nowadays. They tailor make networks and numbers of hosts that they can give out to users, basically, in a company. Okay. Anything else? Yes.
In the ospfd.conf file, import host name and password.
They should all be the same. So leave them at default, and don't mess with them. They should all just work for everybody.
Host name and password in there.
So you can make it more secure. So you can create a network in which the OSPF protocol actually works on approved hosts. So unless you have the correct password in there, then if you try to insert another computer in the network that throws some bogus, that advertises some bogus networks, then it won't actually be able to connect and talk to the rest of the OSPF routers because the password in that configuration file will be wrong. Yeah? Anything else?
Why we use the public addresses?
Because we can.
We have too many.
Yes, so good question. All right, so we're using the public addresses just to show CIDR and basic principles of networking. later on in the next lab sheet if you want to expand it, because the next lab sheet is sort of like a coursework, okay? I will give you some basic principles of operation for it, so some things that you need to have created, but then past that you can create your own computers, you can create VLANs, you can create private IP addresses, you can NAT behind an interface if you like, and you can do whatever you like, and you can create virtual machines in the cloud that will be on private IP addresses. Okay, I just wanted to show you some basic principles of networking on this, and the reason that we're working with networks 30, 31, and 32 is because basically we have the addresses, so why not use them? And the reason why we have the addresses is thanks to a man called Philip True, that we should have a statue of at some point. You know. So he is a system administrator, and around the end of 80s, beginning of 90s, or whenever the IP addressing scheme came out, he thought it's going to be a great idea and this thing will really catch on. So he claimed an entire Class B network for the University of Portsmouth. So we have 65,500 IP addresses to play around with. It's a terrible waste and terrible privilege as well. Yes? So we have them, why not use them? All right. Anything else? Yes.
So, we are using OSPF. Why not RIP?
If you want, you can use RIP if you like. RIP is slower than OSPF. I generally don't like it. Okay, it has slower conversion times, converging times. It's the simplest one that we can use because some people here will not have any previous networking knowledge. So we're just really playing it safe. Okay. If you want later on at the next lab sheet, you can change it to whatever else you like. Just make sure that you explain what you did. Yeah, I mean, Quagga supports other routing protocols as well, obviously. Yeah. Any other question? Yes.
In Jabra.conf file, there is another configuration for do break address. So do we usually need to break interface information in Jabra.conf?
No. So those configurations are usually used for security purposes, and we're trying to make it as simple as possible here. Okay. Anything else? All right then. That's it. Thank you very much.